Yeah. Today topic is series solution of differential equations. Series solution of differential equations. Differential equations. See, previously what we have studied, we solved constant quotient differential equations, right? First part. Second one, variable quotient differential equations. Variable quotient means what? What type? Cauchy homogeneous. Cauchy homogeneous equation, Legender's homogeneous equation. In those differential equations, derivative coefficients are variables in terms of x. So that is some particular form only. Cauchy and Legender having some particular structure, but variable quotient problems. So we studied solution of higher order constant quotient differential equations. Next one, solution of variable quotient differential equations of a particular structure. Okay, and some solutions we are getting. That is, what is the solution type? Y of x equal to some c1 e power x plus c2 e power minus x plus sin x minus cos x, like that. That means the solution contains some particular functions. Solution is having some closed form solutions. What is meant by closed form solutions means involving some standard functions. Solution is involving some standard functions. Okay, but there are some differential equations for which the previous techniques all will not apply. The previous techniques are not applicable. We cannot apply Cauchy's method, Legender's method, or e power x method, sin mx, cosine mx, all those methods, as well as method of variation of parameter also not applicable. Method of variation of parameter also not applicable. For such type of differential equations, we required a series solution. We required a series solution of the differential equation. So what is this? When a variable quotient differential equation, variable coefficient, this is particularly, okay, variable quotient, when a variable quotient differential equation is not having a closed form solution, that is, what is meant by closed form solution? Having some standard functions, then we find the solution of differential equation as series solution. Find the solution of a differential equation as a series solution. A simple brief introduction about why series solution is required. I will show the examples where all the previous methods not applicable. So we have to apply a series solution. Now, before going to series solution, some standard definitions are there. What is the first one? Ordinary and singular points of an equation. Ordinary and singular points of a differential equation. What is the theory here? First thing, see, you have, these are the short questions. Definitely there will be a short question in this topic. Consider a variable coefficient. In particular, say I'm considering second order differential equation, second order linear and homogeneous. This is also important. Homogeneous differential equation. What is the differential equation type? Second order homogeneous differential equation type. Some coefficient into second derivative, some coefficient into first derivative, some coefficient into y, equal to what I told, what I have given, homogeneous. Remember, variable quotient first part, and second order differential equation, and linear and homogeneous. You know what is meant by homogeneous? Right side function is 0. Right side function is 0. Here, always remember this differential equation, second order differential equation means what? This quotient should not be 0. Here, a naught x never 0. A naught x never 0. This is equation 1. Now, dividing this equation 1 divided by a naught x. Let me divide 1 divided by a naught x. Okay. Then what is this? Becomes y double derivative plus a1x over a naught x y dash plus a2x by a naught x y equal to 0. Equal to 0. This is equal to y double prime plus, I will denote this fraction as p of x and the next one as q of x, y equal to 0. Equation 2, which is called normal equation or standard form, or normal form, or it is also called as canonical form. Okay. Here, what is p of x? Clearly, here p of x is what? a1x over a naught x. Q of x equal to what? a2x over a naught x. Remember, a naught x is never 0. Okay. Now, see the definitions. What I told, what is this one? Ordinary, and another one is singular point. Ordinary point and singular point of a differential equation. How to define? First, let there be a one point x naught belongs to the domain I. Solution domain. I stands for some interval. Okay. Let x naught belongs to I. I is the given interval. Okay. And one more important point is a1x function and a2x function are analytic. What is the meaning of the term analytic here? You will get in the complex next unit, complex variables. A1x, this function and this function, a1x and a2x are analytic. Analytic means that is a1x, a2x are differentiable. Derivatives exist, that's it. Okay, are differentiable at x naught and in a neighborhood of x naught, and in a neighborhood of x naught. That is the meaning of analytic function. What is the meaning? a1x, a2x, both are differentiable functions at x naught. Not only at x naught, in its a small neighborhood also these functions are differentiable. Okay, that is the meaning of analytic. Okay, analytic means at a point the functions are differentiable, as well as in the small neighborhood of the point the functions are differentiable. That is the meaning of analytic. Okay, then the first definition, ordinary point. Say the definition. What I have considered point A now. A point x naught belongs to I is said to be ordinary point. Of equation 1. What is equation 1? Standard equation, our standard equation. This one, or this equation. X naught is called ordinary point of equation 1 if a naught of x naught not equal to 0. A naught of x naught not equal to 0. This is ordinary point is also called as regular point. Ordinary point is also called as regular point. Also called as ordinary point is also called as regular point. And what is the condition here? Remember, this a naught of x is there now here in denominator, a naught of x, a naught of x. Substitute here x equal to x naught. That should not be 0. That means what? All the points, this a naught x naught, a naught x, a naught of x naught. Substitute the point x naught in a naught x. If it is not equal to 0, that point is called regular point or ordinary point. Next one is singular point. Singular point. The definition is same. A point x naught belongs to the given interval I is said to be singular point. Is said to be singular point of equation 1 if, what is this? It must be 0. A naught of x naught equal to 0. A naught of x naught equal to 0. When a naught of x naught equal to 0, then what happens? The nature of the differential equation becomes changed. That means when a naught of x naught is 0, this entire double derivative is vanished, right? So that such type of point is called singular point. That means what? In this equation, see, in this equation, if a naught x equals 0, the differential equation does not exist. The denominator is equal to 0 in the function. That means p of x and q of x are not defined at the point x naught. So a naught of x naught equal to 0 called singular point, not equal to 0 called regular point. Okay, for examples, example 1, 1 minus x square y double dash minus 2x y dash plus n into n plus 1 equal to 0. N into n plus 1 equal to 0. Here, let me write first. What is a naught of x? 1 minus x square. What is a1x? Minus 2x. What is a1x? Minus 2x. Here y will be there. And what is a2x? What is a2x? N into n plus 1. Okay. Now, what is this? Set to get the points. First, a singular point. Set a naught to get x naught points. A naught of x naught 0. 1 minus x square equal to 0. So x equal to what? Plus or minus 1. Therefore, at x equal to plus or minus 1, what is a naught of x? 0. Therefore, x equal to plus or minus 1 are singular points. X equal to plus or minus 1 are singular points. Okay. Next, and one more point is what? Saying, all of you remember, the functions must be analytic. Analytic means differentiable. Clearly, here, a1x, that is negative 2x, a2x, that is constant, n into n plus 1, are analytic. Analytic means differentiable. Differentiable at the point, analytic at what is the point? Singular points at x equal to negative 1 and plus 1. That means at these points, what is a1x derivative? Minus 2. a2x derivative 0. Both are exist at minus 1 and 1. So those are analytic. Okay. This is first example. And let me take second one. X square y double dash plus ax y dash plus by equal to 0. AB are constants. AB are constants. Here, what is a naught of x? X square. A1 of x? Ax. A2 of x? B. So what are the points set? A naught x equal to 0. That means x square equal to 0. That is nothing but x equal to 0. Therefore, x equal to 0 is the singular point. X equal to 0 is the singular point. And what is this? A1x, ax, its derivative is a. And a2x, b, its derivative is 0. Or analytic at x equal to 0. At the singular point, the function must be analytic. That is the rule. Okay. Now, another important next step, moving towards the next topic. See, you write like this. Let the point x0 we are considering in the given interval x0 belongs to I be a singular point. Be a singular point of equation 1. Be a singular point of equation 1 where a1x, a2x are analytic. This is compulsory condition. Or analytic at what point? At x0. At x0. Okay. Now consider the standard form or normal form. Okay. Standard form of equation 1. That is, what is standard form of equation 1? That is vector equation 2. Okay. What is that? Y double dash plus P of x into y dash plus Q of x into y equal to 0. What is that? This is equation 2 I have taken. Do you remember, right? Where what is P of x is nothing but a1x by a0x. Q of x is a2x by a0x. a2x by a0x. Why I am writing again? See. What is importance? I will change now. This is now rewrite equation 2 as y double dash plus what is the singular point here? x0 is the singular point. x0 is the singular point. Then you write this equation 2 as some p1x function. Get x minus x0 term in the denominator into y dash plus q1x by x minus x0 whole square into y equal to 0. You rewrite like this. And for your clarification, I will write like this. Okay. How? Question mark. So rewrite equation 2 as I am writing here. Y double dash plus what is actually P of x into y dash will be there. I will take this P of x multiply divided by x minus x0 plus next Q of x by I will write x minus x0. This is y. Q of x into y. I will multiply divided by x minus x0 whole square. X minus x0 whole square. So this equation now can be taken as P1x by x minus x0 plus into y dash Q1x by x minus x0 whole square into y equal to 0. This equation is important. Equation 3. Where what is P1x now? What is P1x? This is P1x and this is Q1x. Okay, P1x is what? X minus x0 into P of x. And what is Q1x? Is x minus x0 whole square into Q of x. X minus whole square into Q of x. And what I can write, this is x minus x0. What is P of x actually? A of x by a0x. Isn't it, right? And next one, what is Q1x? X minus x0 whole square. Q of x is what? A2x by a0x. So you remember this equation. You remember now this equation. Y double prime plus P1x by x minus x0 when x0 is the singular point. When x0 is the singular point, equation 1 can be altered as y double prime plus P1x by x minus x0 into y prime plus Q1x by x minus x0 whole square into y equal to 0. When this can be possible? When x0 is the singular point. when x naught is the singular point. Why we are writing this differential equation? Why we are rewriting this differential equation? To define some concept. What is that concept? First definition, regular singular point. First definition, regular singular point. What is the definition here? What is a singular point? X naught, right? A singular point x naught, a singular point x naught of equation 1, nothing but equation 3 also it is. Equation 1 is said to be regular singular point, is said to be a regular singular point if and only if the functions, what are the functions? P1x and Q1x, which are where these P1x and Q1x are in equation 3. The functions P1x and Q1x of equation 3 have removable discontinuities at x naught and become analytic when these discontinuities are removed. When these discontinuities are removed. This is original definition. In other words, I will explain after writing this one. In other words, the functions P1x, and Q1x can be expanded in Taylor series. About the point x naught. This is it. This is simple. You remember this. Okay. Now I will explain. What is the thing here? Regular singular point. When this is the singular point is x naught is the singular point, and it is called regular singular point. When it is called regular singular point in this differential equation 3, this P1x function, this Q1x function, both are having removable discontinuities. What is meant by removable? See, discontinuity means what? The function is not defined at that particular point, and it is removed. Removable means that discontinuity can be removed. It is possible to remove that discontinuity. Okay. Then when I remove the discontinuity, then the functions P1x and Q1x must be analytic. Analytic means what? It possesses derivatives. Analytic means what? It possesses derivatives. Then, in other words, instead of writing this definition, removable discontinuity and so on, the functions P1x, this function P1x and Q1x, both can be expressed in Taylor series expansion. About the point x equal to x naught. That means about the singularity. That is called regular singular point. Another one, irregular singular point. Irregular singular point. What is the definition of irregular singular point? A singular point that is not regular. That's it. A singular point x naught of equation 1 is said to be an irregular singular point if and only if x naught is not a regular singular point. X naught is not a regular singular point. That is, or in other words, how can I write in other words? In other words, the functions, what are the functions? P1x and Q1x. The functions P1x and Q1x cannot be expanded in Taylor series. About the point x equal to x naught. Now, to understand this concept, let us see one example. X square y double dash plus xy dash plus x square minus n square. X square minus n square into y equal to 0. N is constant. Okay. The question may be, classify the singular points. Classify the singular point of the differential equation. And all of you watch this, observe this differential equation. X square y dash xy dash, up to it is of Cauchy form, but this is not Cauchy structure. Now, can you solve using our previous techniques? Not at all possible. Like previous examples also. What is those examples? X square y double dash ax y dash plus by equal to 0. I think this is a Cauchy equation. And coming to here, this first equation, it is not Cauchy equation, variable quotient of none of the form structures. So it is not possible to find solution. So series solutions are required. Okay, now coming to this one, classification of singular point. First thing, what is the differential equation? X square y double dash xy dash plus x square minus n square into y equal to 0. First, identifying what is a singular point. Here, a naught x equal to x square. I need this much is enough. Then a naught x equal to 0 implies x square equal to 0. That means x equal to 0. Therefore, x equal to 0 is the singular point. X equal to 0 is the singular point. One thing is, first one is fixed. X equal to 0 is the singular point. Then what I have to do? I have to express the differential equation in what form? This structure. What is the structure? Y double dash plus P1x by x minus x naught, Q1x by x minus x naught whole square. I have to express in that form. So for that, let me write equation. Equation can be written as y double dash plus x by x square y dash plus x square minus n square x square y equal to 0. Now this is the form. What is the singular form? I have to convert what structure I have to convert. Okay, one more step I will write y double dash plus 1 by x into y dash plus x square minus n square by x square y equal to 0. Now check, is it this form? Y double dash plus P1x by x minus x naught y dash Q1x by What is this? Must be x minus x naught whole square y equal to 0. Okay. Is of the form. Now both are same. Yes. What is here? X naught equal to what? Here x naught equal to what? 0. So when I put 0 here, automatically this one is of the form. Got it? Is of the form this one. Therefore, what is P of P1x? Therefore, what is P1x? 1. Right? And what is Q of x? What is Q1x? X square minus n square. X square minus n square. Now, this P1x is 1. And this is x square minus n square. These functions are anywhere undefined. P1x and Q1x are anywhere undefined. Yes? No. Always defined. These functions are always defined everywhere. Here are P1x are analytic everywhere. Analytic everywhere. At x not equal to 0 also. Analytic everywhere. That is, what is the meaning of this? P1x equal to 1. Like constant can be expressed in terms of Taylor series. Q1x equal to some another function. X square minus n square or expandable in Taylor series. Expandable in Taylor series about x not equal to 0. About x not equal to 0. When expandable in Taylor series means what? When expandable in Taylor series means what? Expandable in Taylor series means what? Therefore, x not equal to 0 is what? Regular singular point. Regular singular point. Regular singular point. Okay, is that clear? X not equal to 0 is the regular singular point. This is one example. Now, let me consider another example to get more clarification on this regular and irregular. Let me take, you take this. X cube into x minus 2 y double dash plus x cube into y dash plus 6y equal to 0. 6y equal to 0. Okay. Now, what is here? What is a naught? X cube into x minus 2. Done. Now, I have to first find singular points. A naught x equal to 0 implies, that means x equal to 0 comma 2 are the singular points. Are the singular points. Are the singular points, right? So first one, let me take one by one case. What is the equation 1? Differential equation can be written as, to decide whether regular or irregular singular point, I have to rewritten, can be written as, what is that equation? Y double dash plus x cube by x cube into x minus 2 y dash plus 6 by x cube into x minus 2 y equal to 0. Y equal to 0. Right? Okay. Here there are, since there are two singular points, 0 is there and 2 is there, one by one let us consider. Okay. Let us consider, that means let us discuss the type of singularity. Let us consider, what is the singularity I will take? Let us consider the singularity. Let us consider this singularity. What is that? X equal to 2. Let me take first x equal to 2. Then x equal to 2 means I have to write what structure? Then see, then differential equation must be written of the form, must be written of the form, must be written of the form. What is that? Y double dash plus P1x by x minus 2 y dash plus q1x by x minus 2 whole square y equal to 0. X minus 2 whole square equal to 0. So let me consider in that form. So this equation can be taken as y double dash plus 1 by x minus 2. Correct? Y dash plus 1 by x minus 2 y dash plus. Next, what is I have to get x minus 2 whole square now? So 6 into, I will write 6 into, what happened? Yeah, 6 into, in denominator, I have to get x minus 2 whole square. That's it. So I have to write here x minus 2 whole cube and x cube and x cube. Is that clear? Here x cube gets cancelled. X cube gets cancelled. And what about q of x? Yeah, I have to get this structure again. No, not this. So let me write first. This is x cube. X minus 2 whole square I have to get. Therefore, there must be 1 x minus 2 will be here. Done. Into, no, not this. No need of this one. And I have to get only x cube here. I have to get only x cube here. Okay. Into y equal to 0. Into y equal to 0. So what happened here? This implies y double dash plus 1 by x minus 2 y dash plus, I will write like this one, see, x minus 2 by x cube. I will take x cube into numerator, whole square into y equal to 0. Here, what is p1x? 1. What is q1x? 6 into x minus 2 by x cube. X cube. These two functions have Taylor series expansion. Taylor series expansion about, what is the singularity here? About x equal to 2. See, this is constant, always continuous. This function particularly, I'm talking about this function, Taylor series not exist at x equal to 0 because denominator x cube is there. But what is here the singular point? X equal to 2. So Taylor series exists. Taylor series, these two functions have Taylor series expansion about x equal to 2. Therefore, x equal to 2 is the regular singular point. 2 is the regular singular point. Regular singular point. Now let us consider the singular point. Now consider the singular point x equal to 0. Consider the singular point x equal to 0. Then what I have to write the equation as? What is our equation? Y double dash, what I have written? X cube by x cube into, what is the, actually, let me write our equation. What is the original equation? Original equation is x cube into x minus 2 y double dash plus x cube y dash plus 6y equal to 0, right? That's the equation. I have to write, you must remember the structure. Now what is the singular point? This one, singular point. So first let me divide x cube by x cube into x minus 2 y dash plus 6 by x cube into x minus 2 into y equal to 0. Then this implies y double dash plus 1 by x minus 2 y dash 6 by x cube into x minus 2 y equal to 0. we must have the form x equal to 0 is a singularity. You write like this. For the singularity, x equal to 0, we must have the form. What is the form? Y double dash plus p1x by x minus x naught. X naught value is what? 0. Y dash plus q1x by x square y equal to 0. Right? Still any doubt? X naught value is 0 here. Now, to get that form, I have to, what is our alternations now? Y double dash plus. In denominator, I have to get x. So, first let me write 1 by x. I will take x minus 2 to the numerator, 1 by x minus 2, and I will multiply it by x. Is that clear, right? Multiply divided by x. Right? Again, x gets cancelled. I will get the same form here. Now, same logic here also. 6 by x minus 2 taken here, and x square will be there, and one more x here. Then again, same form. This structure can be taken as, I will take x into x minus 2 into numerator part, x square in denominator part, y equal to 0. That structure is there. Now, here, what is p1x? Here, p1x is what? This entire is p1x. 1 by x into x minus 2. What is q1x? What is q1x? Sorry. This is not 1 by x. X into, I think, correct? This x is in numerator now, right? So, x by this one, and q1x is 6 by x into x minus 2. 6 by x into x minus 2. Here, p1x is having Taylor series expansion. Having Taylor series about what point? What is the singularity we are discussing? 0. Yes, this function is defined. X by x minus 2 is defined at x equal to 0. Doesn't matter. But this is important. But q1x 6 by x into x minus 2. Here there is x. Here there is x. Is not having Taylor series. Not having Taylor series about x equal to 0, because you write q1x equal to 6 by x into x minus 2 is not defined at x equal to 0. Not defined at x equal to 0. Therefore, what is the singular point? X equal to 0 is irregular singular point. Irregular singular point. Irregular singular point. Now, you take assignment. Classify the singularity. Classify the singularity. You take first one. X square y double dash plus, I think I told that. Yeah. Only 2 problems I have taken now. Yeah, you take this. Ax plus by x square y double dash ax y dash plus by equal to 0. A, B are constants. Second one. 1 minus x square y double dash minus 2x y dash plus n into n plus 1 y equal to 0. N is constant. N is constant. Third one. You take sines and cosines here. Plus sin x by sin x y dash plus cosine x y equal to 0. Cosine x y equal to 0. Okay, this is one topic. See, in this topic, definitely there will be a short question. There will be a short question, and the concept is important about regular singular point and irregular singular point.